All right, so we've got a question about two different definitions of the scale product and how they turn out to be equal. And we're going to do this in two dimensions, thinking about having vectors that have coordinates, but the result here can be extended into three dimensions as well. So we got here vector A is basically ending at a certain point, A1, comma, A1, A2. We got a vector B over here, and we can make it longer or shorter, whatever, going at the point B1, B2. And if we connect like that, it forms a triangle. And that third vector right there, from AB, from point A to point B, is B minus A. And the way I know that is because I'm starting at A1 and I'm ending at B1. So the vector B minus A is equal to B1 minus A1, comma, B2 minus A2, which would be, from the origin, would be a parallel line down there, but I'm just sliding it up so that it touches the edges of the other triangle. So that's just one of the ideas that when you subtract B minus A, you can imagine that resulting vector as going from A to B, because you're just seeing how far apart the x values are and how far apart the y values are. And you have to remember that vectors can be translated all around the plane to wherever you want them. And so I just translated it to stick it on there. Okay, so we're going to try to use the properties of the scalar product and the cosine theorem to show that the geometric and algebraic definitions are equivalent here. And so we're going to define this as our angle theta. What I know from the law of cosines, or the cosine rule, is that when you have the cosine rule, you can say that a squared plus b squared minus 2ab cosine c, cosine theta here, is going to equal b minus a squared. You have to be really careful because the letters can get mixed up as vectors or as lengths here. So when I'm talking about the cosine rule, I'm talking about actual like lengths on a triangle. So I'm going to use our absolute value symbol to just remind everybody that we're talking about lengths. Okay. So then the absolute value of a squared I can write as a dot a. The absolute value of b I can write as b dot b. And here I've got two absolute a, absolute b cosine theta equals absolute value of b minus a. I don't really have, I guess I do. I can use b minus a dot b minus a, just like I did with the other ones. So what I'm using here is I'm using that property of the scalar product, which is that a dotted with itself is the magnitude of a squared. I'm just using that over and over again. Then if I distribute out b minus a and b minus a, I'll get a dot a plus b dot b minus 2 magnitude a magnitude b cosine theta equals b dot b minus 2 copies of a dot b plus a dot a. Now I can subtract a dot a from both sides. It's just a number. Subtract it from both sides. Subtract b dot b from both sides. B dot b from both sides. And I've got negative 2 magnitude a, magnitude b, cosine theta equals negative 2 a dot b. Divide both sides by negative 2, and I have the desired result. So the key intuition here is that when you draw two vectors a and b, that if you subtract them, the resulting vector will connect between the endpoints of your two original vectors. Just think about the components there and why that makes sense. b1 minus a1, b2 minus a2, that tells you how far apart the x values are and how far apart the y values are. You can kind of think of it as in terms of like rise and run. Okay, you see how that's like your run and that's like your rise. Once you have that, you're just setting up the cosine rule, and you're just using the two properties that I used. Was this a dot a is the magnitude of a squared, and then the other one I used is that you can distribute. A dotted with b plus c is a dotted with b plus a dotted with c. And you can verify those properties for yourself just by writing down some vectors in terms of their components and performing the operations on either side of the equal sign and seeing that you get the same thing. So here we just proved that the dot product, the scalar product, has this geometric definition, and that's the same thing. A dot b over here on the right side is the same thing as just going a1 b1 plus a2 b2. So this is a really powerful way for you to find angles between two vectors, and it does extend up into 3 dimensions just with including an a3 b3 here at the end of your formula. So thanks for watching. Let me know if you need anything else.